We're on lecture number 7 for CIVE 360, and last time we introduced the concept of statically indeterminate problems, mainly statically indeterminate axially loaded bars, and that'll be our abbreviation for it just so we don't have to keep writing it all out. What we found is that we need to use more than just statics, and the first one of our big three tools that we'll be using is statics. The solid has to be in equilibrium, obviously, but the second one is stress-strain law. And the way that that manifests itself is delta is PL over AE. So we're going to be actually using that to solve some of our practical problems. The third tool that we need is compatibility, and I'm going to abbreviate that. And compatibility is basically that the deformed geometry has to be acceptable. There can't be any gaps or voids in that. So there are three tools that we use to solve these problems. Now it also turns out that there are three of something else. So there are three main types of problem for an axially loaded bar. SI axial bar. And what we're going to do is we're going to go through each one, probably perhaps not start to finish, but we're going to set these up so that when you work on these as homework, you'll get a chance to start on these and take them all the way through. So here they are. We're going to do these in order. And basically, they're just in order that I'm going to introduce them. The first is called the fixed bar. That's the one that we introduced last time. The fixed bar. What that means is that you're going to have a support at the left-hand end and the right-hand end that are both going to be fixed. And we're going to show this by example. So we're going to go ahead and set a fixed support at that location. And then we're going to have a couple of segments here. So I'm going to go ahead and put a couple of dashed lines. That's going to indicate differences. And then we're going to fix that particular location. We're going to call this point B, because remember we reserve A for the area. This is going to be C, D, and then the right-hand support is going to be point E. Now, maybe that's not as good because we've also got the modulus elasticity, but we're not going to worry about that because we don't use it as much. In fact, that point's going to be kind of a little bit superfluous. We're going to go ahead and give distances then. So from B to C, it's going to be 6 inches. From C to D, it's 4 inches. And from D to E, we're going to call that 8 inches. Then it's made of two different materials. BD is bar 1, and bar 1, in fact, let me put the parentheses over here. That's going to be bar number 1, and then DE is bar number 2. So all the properties from B to D are going to be the same. So BD, and that is bar number 1. It has two properties that we're interested in. The first is that the area, and that's going to be 4 square inches. And then the modulus elasticity is 20,000 KSI. Then D to E is going to be material number 2, and that has an area of 1.5 square inches. And then the modulus elasticity is 10,000 KSI. So those are the properties, and then our loading, we're going to put two of them on here. At point C, we're going to have a 10 kip load. And then at D, right at the joint, we're going to have, pulling this way, of 4 kips. Now normally when we do this and we draw the arrow, that means that the loading is being applied right at the joint. So let's note that. So the 10K and 4K loads are exactly at the joint. By the joint, we mean the connection point between the two different bars. Now, in this case, C is not a connection point. It's just an internal point where we're going to be applying the load. Now, almost always, the problem statement will be find the stress in all bars and then find the displacements. So we want to find the stress for all bars. And then we also want to find the displacement. So find delta at C and delta at D. That's a pretty comprehensive order about what we're going to be trying to find. Now, the reason that this is statically indeterminate, of course, is we have one statics equations and two unknowns. We don't know what the reaction at B and E are going to be. But we do want to start with those three items. So I'm going to go ahead and use letters this time. The first thing that we want to do is statics. So we want to set that up. Now, here is a huge hint when you're setting up the statics. And it's going to make things a little bit easier for you. I want you to draw the left-hand reaction going left. Now, again, in your statics class, you probably learned you can draw it however you want, and the sign will come out in the end. But what we're going to do is I'm going to come up here, and I'm going to call that value the reaction at B, and we're going to draw that going to the left. So that's what I mean by the hint. So let's put that up here, star, because that's going to make things a little bit nicer for us. Now, there is another reaction at E. This one I don't care about. You can draw it however you want. But I'll go ahead and draw it for this purposes of this as also going to the left, and that would be the reaction then at E. Now, the statics part you might think is just going to be global equilibrium, and that's partially true. So the statics part, we're going to put a double arrow there, and there are two parts of statics. In other words, we're going to do equilibrium on two levels. The first one is just the global statement of equilibrium. And that is sum of the forces in the x is going to be equal to 0. And let's take forces going this way as being positive. So now if I look at my entire structure, it's basically its own free body diagram. I have RB and RE going to the left. Those are negative. So I have minus RB minus RE. Then I have plus 10 minus 4. So plus 10 minus 4 is all going to be equal to 0. And that is our global statement of equilibrium. And again, that's fine, but this is one equation and two unknowns that we have. So one equation and two unknowns. And it is the only equation of statics for the entire system that we can use. And that's why it's statically indeterminate. We have one more unknown than we have equations of equilibrium. So that is the global, and that's certainly going to be something that we need to have met when we finally do our analysis. But there's a more important application of statics, and that is to get the internal bar forces in each segment of our problem. Now, what do we mean first off by segment? That means you're going to have to look at the problem and ask yourself, does the area change? Does the modulus elasticity change? Or does the force change inside that segment? So if we go back up here and look at our problem, B to D, let me jot this over here, BD has the same A and E. But we have a point load at C, and that's going to change the internal bar force between BC and CD. So I'll write it PBC is not going to be necessarily the same as P from C to D. So basically, whenever there's going to be a point load, you need to end your segment there. So you count up how many pieces you have. And in this case, we have 3, BC, CD, and DE. So when we say internal bar forces in each segment, so we ask if does A, E, or the force change. That's our indicator about where we need to have a segment. So in this problem, there are going to be 3. There are going to be 3 subsegments. So what we need to do is apply statics to that. So we're going to make 3 cuts. Let me go back up here. Sorry to go back and forth here. We're going to make 1 cut between B and C. We'll call that number 1. Then we're going to make a cut between C and D. We'll call that bar 2. And then 1 cut between D and E. That'll be cut 3. Now when we make the cut, we draw the free body diagram to the left of the cut. So let's write that up. We say we will make 3 cuts and draw the free body diagram to the left. Now, that is not the only way to do this problem, but in my opinion, it is the most efficient, it's the fastest, it's the quickest, and you're going to see how helpful that's going to be. So here's our first free body diagram. There is my first cut between points B and C. Then I've got RB going this way. Now there's no load in between B and C. All we have is the internal bar force. I'll call that P for bar number 1. That's it. That's a free body diagram. So if we do the statics, we find that P1 is equal to RB. So that is a result of statics on the first segment. This is sum of the forces is equal to 0 on the first segment. So not only do we do it for the entire structure, but now we're also doing it for just that first segment. Then the second cut, that looks like this. There's my cut. That wiggly line is where I've made my cut. And again, here we've got a force of 10 kips. We still have RB going this way. So I'm making the cut and draw all forces to the left of the cut. And that is going to be P2. So there's my free body diagram when I made the cut between C and D. And what does that give us? Well, that's going to give us that P2 is equal to RB minus 10. So let me put these in little dash boxes. Those are kind of intermediate useful values that we've got. And then finally our last one, that whole bar is in there. And then part of that last segment, that little squiggle, we've got RB. Sorry about that. We have 10 to the right, and we have 4 to the left. Then there is our P3. And now once again we do our statics and we find that P3 is going to be equal to, and that 4 is going to the left. So we're subtracting off 10 from that. So that's going to be R sub B minus 6. So in each case, we have an expression for the bar force. And notice, every one has only RB. Note, P1, P2, and P3 are all in terms of RB, not RE. And that ends part 1 for today.